Atlas is now moving very close to the Sun. This is the third object we've confirmed that came from beyond our solar system, and it's speeding through the inner part of our solar system at nearly 68 kilometers per second. It's moving inside where Mars orbits and heading toward the point where it gets closest to the Sun. However, in mid-October, when the Sun lines up in a way that blocks our view, the world's telescopes won't be able to see anything. During this time, Atlas will dive into the Sun's powerful electric field, completely out of sight from Earth. Scientists will only be able to guess what's happening and will have more questions about its strange chemistry, huge size, and unpredictable actions. What happens when an object that might be 50 kilometers wide from another star system crashes into the solar wind at top speed, where we can't see it? The schedule, the dangers, and the mysteries we haven't solved all begin now. Right now, this traveler is making its own path inside Mars's orbit. It's tilted about 5 degrees away from the flat plane where planets travel. Its path is so steep and goes in the opposite direction that it cuts almost straight through the solar system's plane. The tilt of its orbit is 175 degrees, which shows how foreign it must be. Most comets and space rocks move in roughly the same direction as the planets, but this one is a real outsider. It's coming from the opposite direction and crossing the planetary paths at a sharp angle. The speed numbers alone tell us about its constant acceleration. When the Atlas survey first measured it in early July, it was already going 58 kilometers per second. Now, as it goes deeper toward the Sun, that speed keeps climbing and should reach almost 68 kilometers per second at its closest point. Imagine this: a piece of debris from between stars, possibly as wide as a medium-sized city, flying through the solar system faster than any spacecraft humans have ever built. Going this fast, it would cover the distance from Earth to the Moon in just over an hour. It will reach its closest point to the Sun on October 29th at 11:55 UTC. The nearest it will get to the Sun is about 1.36 to 1.4 astronomical units, which is just inside Mars' orbit, but still well beyond Earth's path. Unlike comets that get dangerously close to the Sun and risk being destroyed, this visitor won't dive into the Sun's outer atmosphere. Instead, it skirts around the edge of the inner system, moving through the area where the solar wind and electromagnetic fields are most turbulent. When it's at its closest, it will be in the constellation Virgo, but from Earth, the Sun's brightness will make it completely invisible. The orbit information recorded by the Minor Planet Center confirms it's following a hyperbolic path with an eccentricity greater than 1. This mathematical detail proves it will never come back. Its incoming path, outgoing escape, and the sharpness of its swing around the Sun all show this is a brief, one-time visit. Every kilometer it travels now brings it closer to the Sun's area and further from the only viewing spots that can track its journey. This is how a cosmic intruder moves. Inside Mars, 5 degrees off the plane where planets orbit, speeding up from 58 to almost 68 kilometers per second, with an appointment with the Sun on October 29th. The numbers are exact, the timeline is set, and the chance to watch directly is closing with every hour. From Earth's viewpoint, the calendar looks grim. October 21st, 2025 brings what's called superior conjunction. That's when Atlas passes directly behind the Sun, hidden from every ground telescope and even most space observatories. For the next several weeks, the Sun's glare fills the sky, drowning out any trace of this visitor from interstellar space. Astronomers call this a blackout, a forced silence, where no new information can be collected, no matter how advanced the equipment is. The Sun's disk works like a blinding curtain, blocking not only visible light, but also most infrared and ultraviolet signals. Imagine the frustration. After months of urgent planning, over 120 observing sessions, emergency override programs at major telescopes, frantic communications, and late-night calls, the entire worldwide effort is forced to stop. The geometry is harsh. Solar elongation, the angle between the comet and the Sun, as seen from Earth, shrinks to nearly zero. Even the most ambitious techniques using adaptive optics or trying to observe at dawn and dusk fail. Detectors are at risk of damage, and safety systems trigger automatic shutdowns. The last reliable data comes in around October 18th as the object's apparent distance from the Sun drops below critical levels. Coronagraphs, those special solar observatories designed to block the Sun's blinding center, offer little hope. At magnitude 12, Atlas is simply too faint and too small to stand out against the bright, turbulent corona. Deep background removal and image stacking techniques that work well for brighter objects fall short here. No confirmed sightings have come from SOHO, Stereo, Parker Solar Probe, or Solar Orbiter during this time. Attention briefly shifts to Mars. In early October, orbiters like Mars Express and the ExoMars Trace Gas Orbiter captured a few long-exposure images and low-quality spectra as the comet passed near the red planet. Their viewpoint gave them a brief advantage, one last look before the Sun got in the way. Yet even these datasets are limited. The coma appears as a faint, fuzzy dot. The nucleus can't be resolved, and the tail is invisible to their sensors. Attempts to redirect Mars orbiters to take images during the closest approach to the Sun sparked debate within mission teams. Resource limits, orbital geometry, and instrument safety ultimately win. The opportunity closes. So when does the silence end? The recovery window opens in mid to late November as Atlas comes out from behind the Sun and appears in the dawn sky. By then, it will be moving, away in both distance and brightness, but still within reach of large telescopes and dedicated amateur astronomers. The next important date is December 19, 2025, when the comet makes its closest approach to Earth at about 1.8 astronomical units, just before the winter solstice. Between conjunction and when we can see it again, the story is one of waiting and uncertainty. Every hour lost to the Sun's glare is an hour when the most unusual interstellar object ever recorded could change, break apart, or simply fade away unseen. The scientific clock is counting down, and the world waits for the first signal to break through the solar curtain. The size in this case won't settle into one simple number. Early brightness measurements from dozens of telescopes in both hemispheres suggested a nucleus somewhere between 5 and 50 kilometers wide, potentially the largest interstellar object ever seen. That range isn't a small error. It's a symptom of an object covered in its own activity. The coma, a fuzzy envelope of gas and dust, expands so thickly around the core that even the most powerful ground-based telescopes and Mars-orbiting cameras can't see the true solid body. Instead, astronomers have to guess the mass and volume from indirect clues: how the object brightens, how its light scatters, and how quickly the coma thickens as it nears the Sun. The color is also a changing story. Through June and July, the coma's spectrum looked red, perhaps indicating complex organic grains, or larger, slowly vaporizing particles. By August, something changed. The coma shifted to a strong green color, a shade rarely seen so intensely in solar system comets. Spectroscopic campaigns, including those with the Canada-France-Hawaii Telescope and the JCMT, tracked this change in real time. The cause appears to be a surge in carbon-based molecules, especially C2 and CN radicals, released as the comet's CO2 content vaporized under increasing solar heat. The green glow isn't just visually strange, it's a chemical signature showing that CO2, not water, dominates the outgassing. That alone makes Atlas different from most known comets, whose activity is usually driven by water ice. The chemical picture gets stranger. Spectra obtained from both hemispheres and restricted preprints circulating among specialist teams point toward a nickel-to-iron ratio far outside typical solar system ranges. Nickel lines, strong and persistent, outshine their iron counterparts by margins that suggest an origin in a supernova remnant or the stripped core of an ancient, differentiated planet. If confirmed, this would change assumptions about what kinds of debris survive the journey through interstellar space. The dust itself, as shown by polarimetric studies, displays extreme negative polarization. Light scatters in a way that reveals an abundance of fine, possibly glassy or metallic grains, rather than the silicate material familiar from local comets. The shape is yet another puzzle. Instead of a classic tail, pointing away from the sun, Atlas has a coma that is brightest on the sunward side, with a forward scattering envelope that defies standard models of dust and gas flow. The sun-facing edge shines with a density and texture that has prompted heated debate among observers. Some argue for a jetting phenomenon, others for a layer of highly reflective metal-rich dust. The tail pointing away from the sun, if it exists, remains faint and hard to see a mere whisper against the glare. The light curve, tracked obsessively in the weeks before solar conjunction, adds urgency to the mystery. Instead of dimming as expected, the comet's brightness climbed steadily even as it crossed Mars's orbit and entered the sun's domain. This brightness increase before the data gap, recorded in the final days before the blackout, fueled a storm of speculation across every observer channel. Was it a sign of breaking apart? A new burst of volatile gas? Or simply the exposure of fresh surface layers never before touched by sunlight? Each strange feature size, color, chemistry, polarization, coma geometry has drawn the attention of a sprawling, loosely coordinated observer community. Professional astronomers, amateur sky watchers, planetary scientists, and instrument specialists have gathered in digital forums, racing to figure out the object's secrets before technical limits and the sun's glare-imposed silence. Their findings, arguments, and unanswered questions now set the stage for a deeper confrontation with the limits of our instruments and the boundaries of current cometary science. Magnitude 12. That's the predicted brightness of Atlas as it sweeps behind the sun, fainter than any planet and far below what most solar observatories can detect. For instrument engineers and data analysts, that single number defines the practical line between hopeful thinking and real measurement. Coronagraphs like SOHO's LASCO C3 or Stereo's heliospheric imager are built to block the sun's glare and reveal dramatic outbursts, but their detectors are tuned for objects at least 100 times brighter than this interstellar visitor. Even with heroic digital processing, the surface brightness of the coma falls short. The comet's angular size, just a few arc-seconds at best, makes it impossible to distinguish from the background noise of the solar corona. No confirmed detections have come from any solar-focused spacecraft, not from SOHO, not from Stereo, not from Parker Solar Probe, not from Solar Orbiter. The standard data products, those daily movies of the inner solar system, show nothing but turbulent plasma and the occasional planet. For Atlas, the signal-to-noise ratio remains stubbornly below 1. even when combining dozens or hundreds of images. The comet's faint, diffuse glow is simply overwhelmed by the ever-changing light patterns that surround the sun. Some teams propose a workaround: shift and stack. The concept is elegant in theory. Take hundreds of images, predict the comet's apparent motion across the detector, and digitally align each frame so that any faint moving object adds up while static background features cancel out. On paper, this method can push the detection limit down by a full magnitude or two. In practice, it demands accurate predictions of the comet's path, precise knowledge, and a willingness to sort through massive amounts of noisy data, searching for a single faint smudge. For Atlas, even the most optimistic shift and stack campaigns, 100 frames from LASCO, 50 from stereo, still fall short of a secure detection. The math is harsh. The expected gain in signal-to-noise is overwhelmed by the sheer faintness and compactness of the coma. Instrument safety rules create another barrier. As the comet's solar elongation drops below critical angles, automatic shutdowns activate to protect sensitive detectors from accidental exposure to the sun's disk. No amount of manual override can justify risking a billion-dollar imager for a target that may not even be visible. For ground-based telescopes, the situation is even worse. The sun's glare saturates the sky, and no amount of adaptive optics or horizon skimming can pull the comet out of the haze. Mars orbiters offered a brief glimpse of hope. Their unique viewpoint allowed for a handful of long-exposure images in early October. But by the time the closest approach arrived, their orbital geometry and instrument constraints closed that window. No high-end telescope on Earth, in orbit, or circling Mars remained in position to watch the critical moment when solar heating peaked. For now, the data gap is complete. The world's best coronagraphs and heliophysics imagers are forced to admit defeat. Atlas is simply too dim, too small, and too close to the sun for any direct measurement. During conjunction, the only path forward lies in creative data mining, reprocessing old exposures, stacking images along predicted tracks, and hoping for a surprise after conjunction. Instrument teams are already sketching out backup plans for future interstellar visitors, more flexible safety protocols, dedicated shift and stack pipelines, and perhaps one day, solar observatories designed to chase faint comets through the glare. For now, the boundaries are clear. The object is out there, racing unseen, and the instruments built to catch it have met their match. The moment Atlas swings closest to the sun, a new set of questions comes into sharp focus, questions that go beyond standard cometary models. Among the most vocal are supporters of electromagnetic explanations, the so-called electric universe theorists, who argue that comets aren't just icy relics, but active players in the solar plasma environment. For them, the closest approach is more than a gravitational checkpoint. It's a natural laboratory where the solar wind, electric fields, and charged dust could interact in ways that leave measurable traces. One idea on the table: a sudden burst of activity triggered not by heat alone, but by the object's plunge through regions of intense electromagnetic flux. If the coma's carbon dioxide-rich dust is electrically charged, the sun's field could speed up particles, change the coma's shape, or even shift the trajectory by a detectable amount, effects that would show up as small but real deviations in tracking after the closest approach. Dusty plasma specialists are already drafting diagnostic measurements. Changes in coma polarization, unexpected drifts in the outbound path, or a burst of radio emission as solar wind slams into the dense metal-rich envelope. No one is claiming certainty. These are testable predictions, not declarations. When Atlas reappears in November, every new data point brightness, position, coma structure will serve as a test for mission planners and alternative theorists alike. The next phase is a waiting game with the hope that nature might deliver a verdict on ideas long considered fringe. Astrologers tracking the sky at the closest approach note a rare convergence as Atlas threads the constellation Virgo. It stands in direct opposition to Chiron, with Aries nearby, while Jupiter and Pluto form their own axis across the heavens. Chart watchers interpret these alignments as a grand cross overlaid with kite and grand trine patterns that have long been associated with crisis, transformation, and the search for deeper purpose. Some interpret the comet's passage through Virgo as a symbol of healing through disruption, a reminder that even the most alien visitor can stir ancient patterns of reflection and renewal. For those who follow planetary cycles, the timing resonates. Atlas makes its closest pass by Earth just before the winter solstice, a season marked by darkness turning toward light. The outbound journey brings the traveler into a close encounter with Jupiter by March, a progression that in astrological tradition hints at the possibility of new beginnings and shifting collective priorities. Whether these patterns are read as cosmic metaphor or simple coincidence, they offer a bridge between scientific observation and human meaning-making. For viewers who want to mark the occasion, a commemorative design is available. The story of Atlas continues, woven from both data and dream. As the world waits for its return to view, key questions persist. What drives its unusual behavior? Will the closest approach trigger changes in activity or trajectory? These answers await its reappearance in mid to late November. As the data gap continues, each new observation of Atlas will test our understanding of interstellar visitors and the limits of solar system science. For now, only the archived record stands a reminder of how much remains hidden, even as the evidence grows.